Hello everyone, welcome to my channel Chemistry is Fun. Now in my previous videos I have discussed in detail about chemical bonding. Today we will see some important concepts related to chemical bonding, by understanding which it becomes easier to understand the various chemical bonds like covalent bond, electrovalent bond and so on. The first topic which we will deal in is polarity of covalent bond. Now see, covalent bond is formed by the sharing of electrons. I have discussed earlier, covalent bonding is based on sharing of the electrons. So both the atoms which are forming the bond will share one electron each and thus one bond can be formed. Now this polarity develops if both the atoms which are participating in the covalent bond are not the same. In such case we call it as a heteronuclear diatomic molecule like HCl, hydrogen chloride or HF. So if both the atoms are different, that is if they are heteronuclear, in that case what happens, the electronegativity of the two atoms is not the same. As a result, the shared pair will be attracted more by the electronegative atom. As in case of hydrogen fluoride we can see, fluorine is more electronegative than hydrogen. So the shared electron pair between hydrogen and fluorine will shift towards fluorine side. Okay, so this leads to the development of the polarity. So the atom which has high value of electronegativity will be attracting the electron pair strongly compared to the other atom. So here compared to hydrogen, fluorine will be attracting the electron pair towards itself. So in this way what happens? The fluorine end of the molecule will develop a negative charge because the electron pair, the shared electron pair has moved towards fluorine, and the hydrogen end will develop a positive charge because the electron pair, as we can see in this diagram, this is the electron pair, it has shifted towards fluorine. So fluorine will develop a negative charge. There is unequal sharing which we find here, unequal sharing of the electrons. So here we can find that a polar covalent bond is formed. For this, what is the main key point? The electronegativity of both the atoms, as we see here in case of hydrogen and fluorine, the electronegativity should not be the same. So here the electrons are shared unequally. Therefore, on the bonded atoms, as we can see here, hydrogen, it will develop a partial positive charge, and in HF example, fluorine will develop a partial negative charge. Partial because the electron has not been shifted totally to fluorine, it is just shifting towards fluorine, so it develops a partial negative charge. Now in order to indicate the polar covalent bond, we can use some notations, like we see the diagram, we can find out which atom is more electronegative and to which side the electron pair has moved more. That can be found out by seeing the notations. For example, here we can write, this is hydrogen fluoride HF. This is a single covalent bond between hydrogen and fluorine, and as we have mentioned earlier, the electron pair has shifted more towards fluorine. Therefore it will develop a partial negative charge which is designated by delta minus, whereas hydrogen is deprived of the equal sharing of the electrons, so it develops a partial positive charge called the delta plus. This can also be noted by this sign, arrow sign. The arrow towards fluorine shows that the electron pair has moved towards fluorine. This bond polarity can be described by ionic character. In the covalent bond, ionic character will develop because of this polar nature, and this ionic character will increase as the difference in the electronegativity between the two atoms increases. This we can find out by an example. See, in case of hydrogen fluoride, electronegativity of hydrogen is 2.1. For fluorine it is 4. So the difference in electronegativity is 1.9. In case of HCl, for hydrogen electronegativity is 2.1, as we have seen earlier also. For chlorine electronegativity is 3. So the difference in electronegativity between hydrogen and chlorine is 0.9. So we find that the difference in electronegativity between hydrogen and fluorine is 1.9, whereas the difference in electronegativity for hydrogen and chlorine is 0.9. So the electronegativity difference has decreased from HF to HCl. So with this decrease, we find that the ionic character also decreases. So as the electronegativity difference decreases, the ionic character also decreases. Next topic we deal with will be dipole moment. Till now we have seen the polar nature of covalent bond whenever there is electronegativity difference between the two atoms. This polarity can be expressed by a term called dipole moment designated by mu. And we can define it as the product of the distance separating charges. The charges are of equal magnitude but opposite sign. As we have seen in HF, hydrogen develops a positive charge, fluorine develops a negative charge. Both will be equal in magnitude but opposite sign. So when we have to calculate dipole moment, we have to multiply this magnitude of charges and the distance between the charges. So the distance multiplied by the magnitude of the charge will give us the dipole moment. So the distance between positive and negative centers is called the bond length. So we have to multiply bond length and electric charge, that is Q into D. We get mu. So with this we have calculated what we call as the dipole moment. We designate it by mu. So and the unit, like whatever calculation we do, it has to be given some physical unit. So here the unit is dBy, DEBYE, the unit is dBy. And dipole moment can be explained with the help of magnitude and direction both. So it is a vector quantity. Now sometimes there may be a symmetrical molecule, and symmetrical molecule may have polar bonds, as in case of CO2. Carbon is at the center, it is double bonded to oxygen on one side, and another side also another double bonded oxygen is there. So there is a polarity. If you see the bond in C double bond O, there is a polarity because oxygen is more electronegative than carbon. So this is the direction of the polarity. So delta negative charge will be over oxygen, and on the other oxygen towards the other side. But since it is a symmetrical molecule, linear molecule and symmetrical, so both the dipole moments, they will cancel each other. So as a whole it is non-polar. The molecule as a whole is non-polar, though the bonds are polar. And just opposite we can see that there are some unsymmetrical non-linear polyatomic molecules, that is they are non-linear, so they are unsymmetrical, as in case of ammonia and water. They are polyatomic, more than one atom, more than two atoms. They are unsymmetrical non-linear polyatomic molecules. In this case there will always be a net value of dipole moment. And since there is a net value of dipole moment, they all are polar in nature. Overall the molecule is polar. We can see the examples of ammonia and water. In ammonia you see the nitrogen atom is bonded to 3 hydrogen atoms with covalent bonds. Nitrogen is more electronegative, so the shared pair of electron between nitrogen and hydrogen will be more shifted towards nitrogen. So you see the polarity is shown by the arrow towards nitrogen. In all the 3 bonds this is the case. The polarity is towards nitrogen, the direction will be towards nitrogen. So overall there is a polarity we can show by this arrow. So in this case the calculated dipole moment is found to be 1.46 dBy. So it is a non-symmetrical polyatomic molecule. Unsymmetrical polyatomic molecule which is non-linear. Another example we can see water. Water molecule is a bent molecule, it has a bent structure, you know. Here also the shared electron pair between oxygen and hydrogen will be towards oxygen in both the cases. So the direction of the dipole moment will be towards oxygen. So overall dipole moment is like this. It will be calculated. If when calculated we find out it to be 1.84 dBy. If there are two polar bonds, let's say we want to calculate the resultant bond moments. Then let's say there is a molecule in which A is the central atom and the other two atoms are B and C. So there are two polar bonds. AB is a polar bond, this one, A to B. AB is a polar bond, AC is another polar bond. So AB and AC are two polar bonds as we see in this figure. You can see AB and AC. The angle between them is theta. And the resultant dipole moment, if we have to calculate, we are calculating here the resultant bond moments. So you can use a formula given by mu r equal to square root of mu1 square plus mu2 square plus 2 mu1 mu2 cos theta. So using this formula we can calculate the resultant dipole moment, that is the resultant bond moments. Now see here, mu1 is the dipole moment for AB, mu2 is that for AC, and theta is the bond angle. Then in this case, using this formula you can calculate the resultant bond moments. I hope you have understood the concepts I discussed today. Please subscribe to my video. Thanks for watching. Thank you all very much.